Hello, my dear students. Welcome to Teacher at Home. Today, class, we are going to learn the seventh chapter, motion. Everyday life, we see some objects at rest and some others in motion. Birds fly, fish swim, blood flows through veins and arteries, and cars move. Atoms, molecules, planets, stars, and galaxies are all in motion. We often perceive an object to be in motion when its position changes with time. However, there are situations when where the motion is inferred through indirect evidences. For example, we infer the motion of air by observing the movement of dust and the movement of leaves and branches of trees. What causes the phenomena of sunrise, sunset, and changing of seasons? Is it due to the motion of the earth? Is it true? Why don't we directly perceive the motion of the earth? An object may appear to be moving for one person, stationary for some other. For the passengers in a moving bus, the roadside trees appears to be moving backwards. A person standing on the roadside perceives the bus along with the passengers as moving. However, a passenger inside the bus sees his fellow passengers to be in rest. What does this observation indicate? Most motions are complex. Some objects may move in a straight line, others may take a circular path. Some may rotate, a few others may vibrate. There may be situations involving a combination of this. This chapter, we shall first learn to describe the motion of objects along a straight line. We shall also learn to express such motions through simple questions and graphs. Later we shall discuss way of describing circular motion. Describing motion. We describe a location of an object by specifying a reference point. Let us understand this by an example. Let us assume that a school in a village is 2 kilometers north of the railway station. We have specified the position of the school with respect to the railway station. In this example, the railway station is the reference point. We could have also chosen other reference points according to our convenience. Therefore, to describe the position of an object, we need to specify a reference point called the origin. Motion along a straight line. The simplest type of motion is the motion along a straight line. We shall first learn to describe this by an example. Consider the motion of an object moving along a straight path. The object starts its journey from O, which is treated at its reference point. Let A, B, and C represent the position of the object at different instants. At first, the object moves through C and B and reaches A. Then it moves back along the same path and reaches C through B. Total path length covered by the object is OA plus AC, that is 60 km plus 35 km is equal to 95 km. This is the distance covered by the object. To describe distance, we need to specify only the numerical value and not the direction of motion. There are certain quantities which are described by specifying only their numerical values. Numerical value of a physical quantity is its magnitude. From the example, can you find out the distance of the final position of C of an object from the initial position O? This difference will give you the numerical value of the displacement of the object from O to C through A. Shortest distance measured from the initial to the final position of an object is known as the displacement. Can the magnitude of the displacement be equal to the distance traveled by an object? Consider the example given. For motion of an object from 0 to A, the distance covered is 60 km and the magnitude of displacement is 60 km. During its motion from 0 to A and back to B, the distance covered 60 plus 25, that is 85 km, while the magnitude of displacement is 35 km. Thus, the magnitude of displacement is not equal to the path length 85 km. Further, we will notice that the magnitude of the displacement for a course of motion may be 0, but the corresponding distance covered is not 0. If we consider the object to travel back to 0, final position coincides with the initial position and therefore the displacement is 0. However, the distance covered in this journey is OA plus AO, it is 60 km plus 30 km, 60 km, 120 km. Thus, two different physical quantities, the distance and the displacement, are used to describe the overall motion of an object and to locate its final position with reference to the initial position at a given time. Uniform motion and non-uniform motion. Consider an object moving along a straight line. Let it travel 5 meters in the first second, 5 more in the next second, and 5 in the third second, and 5 in the fourth second. In this case, the object covers 5 meters in each second. As object covers equal distance in equal interval of time, it is said to be in uniform motion. Time interval in this motion should be small. In our day-to-day life, we come across motions where objects cover unequal distance in equal interval of time. For example, when a car is moving on a crowded street or a person is jogging in a park, there are some instances of non-uniform motion. Look at the situations given. If the bowling speed is 143 km per hour, what does that mean? Different objects may take different amount of time to cover a given distance. Some of them move fast, some move slowly. The rate at which objects move can be different. Also, different objects can move at the same rate. One of the ways of measuring the rate of motion of an object is to find out the distance traveled by the object in unit time. This quantity is referred to as the speed. The SI unit of speed is meter per second, represented as the symbol meter per second. Other unit of speed include centimeter per second, kilometer per hour. To specify the magnitude of an object, we require only its magnitude. Speed, we require magnitude. Speed of an object need not be constant. In most cases, the speed of an object it is not a constant. Most cases, object will be in uniform motion, non-uniform motion. Therefore, we describe the rate of motion of such objects in terms of their average speed. Average speed of an object obtained by dividing the total distance traveled by the total time taken. That is, average speed equal to total distance traveled by total time taken. If an object travels at a distance s in time, then the speed is v is equal to s by t. Let us understand this by an example. A car travels at a speed of 100 km in 2 hours. Its average speed is 50 km per hour. The car might not have traveled 50 km per hour all the time. Sometimes it might have traveled faster and sometimes slower than this. An object travels 16 meters in 4 seconds and the another 16 meters in 2 seconds. What is the average speed of the object? Total distance traveled by the object is equal to 16 meter plus 16 meter, that is 32 meter. Total time is 4 seconds plus 2 seconds, that is 6 seconds. Average speed is equal to total distance traveled by total time taken. 32 meter by 6 seconds, that is 5.33 meter per second. Average speed of an object is 5.33 meter per second. Speed with direction. Rate of motion of an object can be more comprehensive if it specifies the directions of motion along with its speed. The quantity that specifies both this aspect is called velocity. Velocity is the speed of an object moving in a definite direction. Velocity of an object can be uniform or variable. It can be changed by changing the object's speed, direction or motion or both. When an object is moving along a straight line at a variable speed, we can express the magnitude of its rate of motion in terms of average velocity. It is calculated in the same way as we calculate average speed. In the case of velocity of an object is changing with a uniform rate. Average velocity is given by the arithmetic mean of initial velocity plus the final velocity of a given period of time. Average velocity is initial velocity plus final velocity by 2, that is v equal to u plus v by 2. Where v average is the average velocity, u is the initial velocity and v is the final velocity of the object. Speed and velocity have same units, that is meter per second. Example, the odometer of a car reads 2000 km at the start of a trip and 2400 km at the end of the trip. If the trip took 8 hours, calculate the average speed of the car in km per hour and meter per second. So the distance covered by the car, that is s, is equal to 2400 km minus 2000 km, which is equal to 400 km. Time elapsed, that is equal to 8 hours. Then V average is equal to S by T. Here S is 400 km by T is 8 hours. 50 km per hour. 50 km per hour into 1000 meter, that is we have to transfer this into meter per second. Kilometer transfer to 1000 meter by 1 kilometer. 1 hour by 3600 second. Okay. So that's equal to 13.9 meter per second. Average speed of the car is 13.9 meter per second or 50 kilometer per hour. Example. Usha swims in 90-meter long pool. She covers 180 meter in 1 minute by swimming from one end of the other and back along the same straight path. Find the average speed and average velocity of Usha. Total distance covered by Usha in 1 minute is 180 meter. Displacement of Usha in 1 minute is 0 meter. Average speed. Total distance covered by total time taken. It is 180 meter by 1 minute. 180 meter by 1 minute into 1 meter. 1 minute by 60 seconds. 1 minute cancel. 180 by 60, that is equal to 3 minutes per second. Average velocity is displacement by total time taken. 0 m by 60 second, that is equal to c2 meter per second. Average speed of Usha is 3 meter per second and her average velocity is 0 meter per second. Rate of change of velocity. During uniform motion of an object along a straight line, velocity remains constant with time. In this case, the change in velocity of an object for any time interval is 0. However, in non-uniform motion, the velocity varies with time. It has different values at different instants and at different points of the path. Thus, the change in velocity of the object during any time interval it is not 0 can be expressed the change in velocity of an object. To answer such a question, we have to introduce another physical quantity called acceleration, which is a measure of the change in velocity of an object per unit time. That is, acceleration is equal to change in velocity by time taken. The velocity of an object changes from an initial value u to the final value v in time t. The acceleration a is equal to v minus u by t. This kind of motion is known as the accelerated motion. Acceleration is taken to be positive if it is direction of velocity and negative when it is opposite to a direction of velocity. So SI unit of acceleration is meter per second. If an object travels in a straight line and velocity increases or decreases by equal amounts in equal interval of time, acceleration of the object is said to be uniform. The motion of the freely falling body is an example of uniformly accelerated motion. On the other hand, an object can travel with non-uniform acceleration. If its velocity changes at a non-uniform rate, for example, if a car traveling along a straight road increases speed by unequal amounts in equal interval of time, the car is said to be moving with non-uniform acceleration. Starting from a stationary position, Rahul paddles his cycle to attain a velocity of 6 meters per second in 30 seconds. Then he applies brakes such that the velocity of the bicycle comes down to 4 meters per second in the next 5 seconds. Calculate the acceleration of the bicycle in both the cases. The first case, initial velocity u equal to 0. The final velocity v is equal to 6 meters per second. Time t equal to 30 seconds. From equation we have a equal to v minus u by t. Substituting the given values u, v and t, above equation a is equal to 6 meters per second minus 0 meters per second by 30 seconds. It is 0.2 meters per second. In the second case, initial velocity u is equal to 6 meters per second. Final velocity v equal to 4 meters per second. Time t equal to 5 seconds. Then a is equal to 4 meters per second minus 6 meters per second by 5 seconds, 0.4 meters per second. The acceleration of the bicycle in the first case is 0.2 meters per second and the second case is minus 0.4 meters per second. Graphical representation of motion. Graphs provides a convenient method to present basic information about a variety of events. For example, the telecast of a one-day cricket match. Vertical bar graphs shown the run rate of a team in each over. As you have studied in mathematics, a straight line graph helps in solving a linear equations having two variables. To describe the motion of an object, we can use line graph. In this case, line graph shows dependence of one physical quantity, such as distance or velocity, on another quantity such as time. Distance time graph. This change in the position of an object with time can be represented on the distance time graph, adopting a convenient scale of choice. This graph, the time is taken along the x-axis and the distance taken along the y-axis. Distance time graph can be employed under various conditions where objects move with uniform speed, non-uniform speed remain at rest, etc. We know that when an object travels equal distance in equal interval of time, it moves with uniform speed. This shows that the distance traveled by an object is directly proportional to time taken. Thus, for uniform speed, A graph of distance traveled against time is a straight line. The portion OB of a graph shows that the distance is increasing at a uniform rate. Note that you can also use the term uniform velocity in place of uniform speed if you take the magnitude of the displacement equal to the distance traveled by the object along the y-axis. We can use the distance time graph to determine the speed of an object. To do so, consider a small part AB of the distance time graph shown. Draw a line parallel to the x-axis from point A and the line parallel to y-axis from point B. These two lines meet each other at point C to form a triangle ABC. Now on the graph, AC denotes the time interval T2 minus T1, while BC corresponds to the distance S2 minus S1. We can see from the graph that as the object moves from the point A to B, it covers a distance S2 minus S1 in the time T2 minus T1. The speed v of that object therefore can be represented as v is equal to S2 minus S1 by T2 minus T1. We can plot the distance time graph for accelerated motion. That is time in seconds 0, distance is 0, time 2, distance 1, time 4, distance 4, time 6, distance 9, time 8, distance 16, time 10, distance 25, time 12, distance 36. The distance time graph for the motion of the car is shown. Note that the shape of the graph is different from the earlier time distance graph for uniform motion. The nature of a graph shows non-linear variation of the distance traveled by the car with time. Thus, the graph shown represents the motion with a non-uniform speed. Velocity time graph. The variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. In this graph, time is represented along the x-axis and the velocity along the y-axis. If the object moves at uniform velocity, height of the velocity time graph will not change with time. It will be a straight line parallel to the x-axis. Shows the velocity time graph of a car moving with a uniform velocity of 40 km per hour. We know that the product of velocity and time give displacement of an object moving with uniform velocity. Area enclosed by uniform velocity time graph and the time axis will be equal to the magnitude of the displacement. To know the distance moved by the car between time t1 and t2, draw perpendicular from the points corresponding to a time t1 and t2 on the graph. Velocity of 40 km per hour represented by the height AC and BD to the time is t2 minus t1. So the distance S moved by the car in time t2 minus t1 can be represented S equal to ACCD, area of the triangle ABCD. We can also study about uniformly accelerated motion by plotting its velocity time graph. Consider a car driven along a straight line for testing its engine. Suppose a person sitting next to the driver records its velocity after every 5 seconds by noting the reading of the speedometer of the car. Velocity of the car in km per hour as well as in meter per second is shown. In this case, the velocity time graph for motion of a car is shown. The nature of a graph shows the velocity changing by equal amount in equal interval of time. Thus, for all uniformly accelerated motion, the velocity time graph is a straight line. You can also determine the distance moved by the car from its velocity time graph. Area under the velocity time graph gives the distance moved by the car in a given interval of time. If the car would have been moving with uniform velocity, distance traveled would be represented by the area ABCD under the graph. Since the magnitude of velocity of the car is changing due to acceleration, distance traveled by the car will be given by the area ABCD under the velocity time graph. In this case of your non-uniformly accelerated motion, velocity time graph can have any shape. Shows the velocity time graph that represents the motion of an object whose velocity is decreasing with time. Shows the velocity time representing non-uniform variation of velocity of an object with time. Then here are some questions are given and also the time. Equations of motion. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during motion, and the distance covered by it in a certain interval of time by a set of equations known as the equation of motion. Where u is the initial velocity of an object which moves with uniform acceleration for a time t, v is the final velocity, s is the distance traveled by an object in a time t, describes the velocity time relation, represents the position time relation. Relation between the position and velocity can be obtained from this. A train starting from rest attained a velocity of 72 km per hour in 5 minutes. Assuming the acceleration in uniform, acceleration distance traveled by the train for attaining the velocity. U is equal to 0, V equal to 72 km per hour, 20 meter per second, T is 5 minutes 300 seconds. A is equal to V minus U by T, 30 meter per second minus 0 meter per second by 300 seconds, 1 by 15 meter per second. 2a is V square minus U square is V square minus 0. V square by 2a, that is 20 meter per second whole square by 2 into 1 by 15 meter per second. It is equal to 3000 meter, that is 3 kilometer. A car accelerates uniform with a 18 km per hour to 36 km per hour in 5 seconds. Calculate the acceleration and the distance covered by the car in time. That is U is equal to 18 km per hour, that is 5 meter per second. V is equal to 36 km per hour, 10 meter per second, and T equal to 5 seconds. A is equal to V minus U by T, 10 meter per second and 5 meter per second. 5 second, 1 meter per second is equal to ut plus half at square, that is 5 meter per second into 5 second plus half into 1 meter per second. 25 meter plus 12.5 meter, that is 37.5 meter. The brakes applied to a car produce acceleration of 6 meter per second in the opposite direction to the motion. The car takes 2 seconds to stop after the application of brakes. Calculate the distance it travels during this time. We have given this A is equal to minus 6 meter per second, T equal to 2 seconds, V equal to 0 meter per second. V equal to U plus AT, that is 0 equal to U plus minus 6 meter per second, U is equal to 12 meter per second. S equal to UT plus half AT square. It is 12 meter per second in 2 seconds plus half minus 6 meter per second into 2 seconds. That is 24 meter minus 12 meter is equal to 12 meter. Thus the car will move 12 meter before it stops after the application of brakes. Can you now appreciate why drivers are cautioned to maintain some distance between vehicles while traveling on the road? Uniform circular motion. When the velocity of an object changes, we say that the object is accelerating. The change in velocity could be due to change in its magnitude or the direction of motion of both. Can you think of an example when an object does not change in magnitude or velocity but only its direction of motion? Let us consider an example of the motion of a body along a closed path. Shows the path of an athlete along a rectangular track ABCD. Let us assume that the athlete runs at a uniform speed on the straight parts A, B, B, C, C, D and D of the track. In order to keep himself on track, he quickly changes his speed at the corners. How many times will the athlete have to change his direction of motion while he completes one round? It is clear that to move in a rectangular track once, he has to change his direction of motion 4 times. Now suppose instead of a rectangular track, the athlete is running along a hexagonal shaped path A, B, C, D, E, F. In this situation, the athlete will have to change this direction 6 times while he completes one round. What if the track was not a hexagon but a regular octagon with 8 equal sides as shown? It is observed that as the number of sides of the track increases, athlete had to take turns more and more often. What would happen to the shape of the track as we go on increasing the number of sides indefinitely? If you do this, you will notice the shape of the track approaches the shape of the circle. Length of each of the side will decrease to a point. The athlete moves with a velocity of constant magnitude along a circular path. Only change in velocity is due to a change in the direction of motion. Motion of the athlete moving along a circular path is therefore an example of accelerated motion. We know that the circumference of a circle of radius r is given by 2 pi r. The athlete takes t seconds to go once round the circular path in radius r. Speed is given as v is equal to 2 pi r by t. When an object moves in a circular path with uniform speed, motion is called uniform circular motion. Now let the stone go on releasing to the thread. That is, if you carefully note on being released, stone move along a straight line tangential to a circular path. This is because once the stone is released, it continues to move along the direction it has been moving to at that instant. This shows the direction of motion changed at every point when the stone was moving along the circular path. When an athlete throws a hammer or a discus in a sports meet, he or she holds the hammer or the discus in his hand and gives it circular motion by rotating his own body. When released in the desired direction, the hammer or discus moves in the direction in which it was moving at the time it was released, just like the piece of stone in the activity described above. There are many familiar examples of objects moving under uniform circular motion, such as the motion of the moon and the earth and the satellite in circular orbit around the earth, a cyclist on a circular track at constant speed, and so on. Motion is a change in position, can be described in terms of distance moved or the displacement. Motion of an object could be uniform or non-uniform depending upon whether its velocity is constant or changing. The speed of an object is the distance covered per unit time. Velocity is the displacement per unit time. Acceleration of an object is the change in velocity per unit time. Uniform and non-uniform motion of an object can be shown through graph. Motion of an object moving at uniform acceleration can be described with the help of following equation: v is equal to u plus at, s is equal to ut plus half at square, 2as is equal to v square minus u square, where u is the initial velocity which moves with the uniform acceleration at a time t, v is the final velocity, s is the distance in time t. When an object moves in a circular path with uniform speed, motion is called uniform circular motion. So that's all about this chapter. If you are interested, please do like, share and subscribe my channel. Okay, thank you.